Okay, excellent. Any questions from last time? Any questions from last time? Okay, so if there are no questions, then let's go ahead. Can you see the screen? Lecture 13 SI425 at your end?
Hello, ma'am.
Yes, please.
Ma'am, last time we studied that every Cauchy sequence is bounded. Is the converse of this statement is also true?
See, for the
Every
real numbers, what can you say about the real numbers? Meaning real numbers in the sense, what can you say about the real line with the Euclidean metric? Is every bounded sequence Cauchy? Not necessarily, right? For example, you know, so I'll just write. For example, let's take this example of the sequence xn as -1 to the power n. Right. So is the sequence xn bounded? Can you see what I have
yes,
written on? Yeah.
yes,
But
ma'am.
is the
Yes.
sequence xn Cauchy? Is the sequence xn Cauchy?
No, ma'am.
It's not, because it's not convergent, right? And by Cauchy convergence criteria in the Euclidean metric, a sequence of real numbers is Cauchy if and only if it is convergent, right? So I'll just write that down.
Okay, ma'am.
Yeah, is that okay? Does that answer your question?
Okay, ma'am.
Yes.
Yes, ma'am. I
Yeah.
understood.
Anything else?
Ma'am,
Yes, please.
ma'am, there was a question in the last assignment. So
Yes.
we were having some problem in showing the if part of that question.
Which question is this?
Ma'am, just a minute, I'll let you.
Meaning you don't have to tell the question number. You have to just tell me what is the question.
Ma'am, it was asking, it was a true-false question. It was said that if a sequence is bounded if and only if every subsequence is a convergent subsequence.
Correct.
So, so the only if an was bounded, we could show that it had a convergent subsequence.
Correct.
If you could please discuss the other part.
Okay. So, you know, I would say that first look at the real line with the Euclidean metric and try to see if the converse is true. Yeah. If every subsequence of a convergent sequence is, if every subsequence of subsequence is convergent, right?
Yes,
Yeah. So, for example, you know, look at the example that you see on your screen. Let's look at xn equal to -1 to the power n. Does this hold true? Every subsequence of subsequence is convergent in this example.
yes, ma'am.
So think a little bit more. Yeah, I would say please think a little bit more. If the problem still persists, then we will talk about it on the Thursday morning session. Is that okay? Yeah, so I would say, you know, work with the real line with the Euclidean metric first. Try to see some examples and then look at the general matrix case. Yeah, is that okay? For now, you know, I would you know, try a little bit more. There's nothing to lose. Sure. Yeah. Anything else? Okay, so if there are no further questions, then let's continue with what we were discussing last time. So we were discussing convergence in the extended real number system, right? Let me quickly recall. Okay, all right. So let's consider xn a sequence of real numbers. So this is a definition. So let xn be a sequence of real numbers, and we say that xn converges to positive infinity if something happens. Yeah. We say that the sequence xn converges to we so far we understand what is the meaning of a statement that xn converges to a real number. Now this is something more. So this is we say that xn converges to positive infinity if for each real number m there is an integer which I am labeling as a positive integer, which is I am labeling as little n, such that the terms of the sequence xn are bigger than this fixed real number m from stage capital N. Yeah, I should write a for. If for each real number m there is a cutoff stage beyond which all the terms of the sequence are bigger than this fixed real number. Okay. Yeah. And another definition. Having understood this, we should be able to say that for a sequence xn of real numbers, the sequence xn is set to converge to minus infinity. What is the meaning of this statement? Minus infinity. If you look at the sequence minus of xn, this sequence converges to positive infinity in the sense described above. Okay, so let's take an example. Let's take xn to be n square, right? So you look at that the sequence xn is not bounded, right? That is evident. So the sequence cannot converge to a real number, right? Because every convergent sequence of real numbers is necessarily bounded, right? So now you investigate whether the sequence xn converges to positive infinity or negative infinity or whatever, right? So I claim that the sequence xn converges to positive infinity. So I have to tell you, so I have to fix a real number m, and I have to find out this cutoff stage as to how far do I need to go in the sequence xn in order to make sure that the terms of the sequence xn are bigger than this fixed real number m from that stage onwards. Correct? So what should I choose capital N to be? So for a real number m, what is that I want? I want xn to be bigger than this real number capital M whenever little n is bigger than capital N. So how should I choose capital N to be? What should I choose capital N? Any suggestions? Somebody wants to suggest something?
Ma'am, n square is greater. May I?
Yes, please go ahead. Yeah.
N square is greater than m means n is greater than root m. So
Correct.
capital capital N can be box of root m plus 1 greater than or equal
Correct.
to.
So the point is that root of m may not be an integer, right? May not be a positive integer. So in order to make sure, you sort of do the following, right? So for capital M, some fixed real number, choose. So given capital M, choose n to be so as you suggest. So I'll write down the suggestion of the student. Square root of m. Yeah, so this is, what is this? This is the smallest integer strictly larger than square root of m. Yeah, choose n to be this, which is the smallest integer strictly larger than square root of m. Yeah, so I am doing all of this to ensure that n that we choose is actually a positive integer, right? Okay, so then for all n, so then I would like this. Yeah, so then the terms of the sequence xn are bigger than capital M whenever little n is bigger than capital N, where capital N is as chosen above. So this tells us that so what is it I wanted to say? Yeah, so capital M here is any arbitrary real number. So this shows that the sequence xn in this example converges to positive infinity in the sense of above definition. Correct? Is that okay? Yeah. So this is one particular choice of capital one that does the job. You may want to sort of choose something else, and that still may work. Is that okay?
Yes,
Yes. Okay. Okay. So in light of this example, let's make the following statement.
Yes.
All right. A sequence that converges to positive infinite needs to be unbounded. So does everybody see that? A sequence that converges to positive infinite cannot be bounded. Why is that the case?
Since
Does
there does not
everybody see
exist,
this? Yes, please. Somebody wanted to say something. Yes, please.
since there does not exist any real number which we can say that the upper bound of sequence, because it is always uh, greater than, and there always exists an integer m where the xn is greater than, so not integer, I'm sorry, I mean the real number m, xn is always greater than, so it's a contradiction then.
Right. So
If we,
Chiranjeev, you are right. Your idea is correct. But how do you say that? So you say that suppose this is not the case. Suppose the sequence is bounded and let the bound be set in capital R, right? So what do you say? How do you arrive at a contradiction? Then the terms of the sequence xn cannot sort of exceed R plus 1 no matter what, right? Things like this. Is that okay?
yes ma'am, that's what I
Yes.
wanted.
So does everybody follow this? So does everybody follow this little sort of observation?
yes,
Is that a yes with everybody? Yeah. So, there's another thing that I sort of wanted to discuss with all of you. So how many of you are here? Only 25 of you. But anyways, I have been browsing through your assignment submissions, and so you should also learn, how to write concisely and precisely. So, for example, so for example, if somebody says that so this a sequence that converges to positive infinite needs to be unbounded, then you should be sort of be able to write down concisely and precisely as to what happens. So I'll give you an example. I think this is a good opportunity to clarify this, because I've seen sort of all of you writing pages and pages and pages endlessly, which is not required. So let me just sort of try to illustrate an example. Let xn be a sequence. So let's say let xn be a sequence of real numbers that converges to positive infinite. Right. So we claim that the sequence xn is necessarily unbounded. Right. So if not, then there is a real number calling R0 such that all the terms of the sequence xn are at most R0, right? And then so what do I say? So then evidently there is no no positive integer such that the terms of the sequence xn are, let's say, bigger than R0 plus 1 for all n. Yeah? So this cannot happen because the sequence is given to converge to positive infinite. So this is a contradiction, and hence we are done. Yeah. So all I'm trying to do is giving you a sample as to how should you write it down. You should provide all the necessary details, be concise, be precise, without missing out on something important. Yeah. So you would get that only if you practice writing. Is that okay? Everybody with me up till this point?
Ma'am, why we have written R0 plus 1? And why not
Anything
directly
bigger
R0?
than R0 will work. Anything bigger than R0 will work. I'm just giving R0 for plus 1 as an example. See, the definition says for each real number m, this is true, right? So in order to say that the sequence xn does not converge to positive infinite, I have to demonstrate one real number m for which this inequality does not hold. And I am saying R0 plus 1 is a candidate. Correct? Anything bigger than R0 will work. Is that okay? Everybody with me up till this point? Shall I take it as a yes?
Yes, ma'am.
Yes? Okay. All right. So then we go ahead. I'll just maybe put a bracket here and sort of y, and this is sort of a digression. Okay. So what is that we said? Any sequence of real numbers that converges to positive infinite needs to be unbounded. How about the converse statement? That suppose that I have a sequence of real numbers which is unbounded. Does that imply that the sequence xn has to converge to positive infinite? Is that okay? Does everybody follow what am I talking about? I'm talking about the converse to this observation that is written in black ink. And I say that the converse is not true in general, and here's an example. So this is not true in general. So let's see an example.
Ma'am, could you explain again that why have we taken R0 plus 1 and not R0? I don't seem to understand this part.
See, xn is at most R0, less than or equal to R0. So anything bigger than R0 will work. R0 plus 1 is just one number which is bigger than R0.
Okay, okay. Anything bigger than R0 works,
Anything
but
bigger than R0 will work.
yeah,
right? Yeah. So
yes.
I'm just giving one example. Correct? Yeah,
Okay.
is that okay? All
Yeah.
right. Okay. I'm glad you asked that. Is everybody with me up till this point?
Yes, ma'am.
All right. Okay. So the now we are looking at the converse statement, and I'm trying to say that the converse is not true. So let's consider the following example. So let's consider the sequence xn of real numbers defined in the following manner. Yeah. So for each little n, let's define xn as follows. Yeah. So I say that xn is 1 if n is even. Yeah. N is an even integer. And xn is, let's say, n if n is odd. So clearly, the sequence xn is unbounded, correct? In this example. And the second observation is that the sequence xn does not converge to positive infinite. Correct? Is that okay? Does everybody follow this? So one can have unbounded sequences which do not converge to positive infinite. Is this okay? Does everybody follow this?
Ma'am, how can we say the second point?
So suppose it does, yeah? Suppose it does. So let's see. You look at the definition. For each odd term, the sequence xn is defined as n, yeah? So let's see. Suppose, let, if possible, the sequence xn converges to positive infinite. Okay, so that means that for each real number m, so let me fix that. So this is saying, for each real number m, the terms of the sequence xn can be are always greater than that fixed real number some stage onwards, right? So I'll choose that real number to be something, yeah. So in particular, this implies that there exists a positive integer such that what happens, the terms of the sequence xn are always bigger than, let's say, 50 whenever n is bigger than n. Is that okay? This statement is true. Everybody agrees with me?
Yes, ma'am.
Now, can this happen?
No,
this
not
happen?
for all.
Sorry?
This cannot happen.
This cannot happen, because xn is 1 for all even terms. Yeah. So even if, let's say, capital N is odd, capital N plus 1 may be even. Yeah. And then xn is 1, takes the value 1 whenever little n is even, right? So this inequality, 1 greater than 50, does not hold true. Yeah. This cannot happen. Is that okay?
Yes, ma'am.
Yes. So I'll just say fill in the proof on your own. Yeah. But do you follow it, right? Yeah. The point is that, but so I see where is this question stemming from? So there is indeed a subsequence of the sequence xn that converges to positive infinite, but the claim is that the sequence xn here itself does not converge to positive infinite. Correct?
Yes, ma'am.
Okay. Yeah, and as I said here, in last time also, I don't have to choose 50 here. What will work? Instead of 50, what is that I can take?
Can we take 2 because 1 is
Anything bigger than 1 will work. Yeah, thank you so much. Anything which is strictly greater than 1 will do the job. Correct? Everybody with me on this point?
Yes, ma'am.
Yes? Okay. All right. So let's see. With this, let's sort of note this down. This example actually tells us something which I'm going to sort of record as a proposition. So suppose mute some background noise. Sorry. So let xn be a sequence of real numbers that is not bounded above. Right? So I'm taking an example of a sequence which is unbounded in R, right? So either it is not bounded above or it is not bounded below, or the other possibility is that it's neither bounded above nor bounded below, right? I'm taking just one of them. So I'm given a sequence of real numbers which is not bounded above. So the above example says that I cannot claim that the sequence xn converges to positive infinite, right? But however, what is that I can say is then there is a subsequence of the sequence xn that converges to positive infinite. Yeah. Is that okay? The statement of the proposition makes sense to everybody present here?
Yes, ma'am. Ma'am,
Yes.
we can always choose this subsequence any matlab, whatever be the sequence. Like there was this question now that Kritika said there is a subsequence such that every subsequence is such that it has a convergent subsequence. So for that we have to show that an is bounded. So on the contrary, if we say that an is not bounded, then it should be unbounded, and we can always choose a subsequence that converges to plus infinity, and hence it is a contradiction that it has a subsequence whose subsequence is not convergent.
See, I will not sort of address that question. That is different, and you're putting two things together. But there might be some link between this proposition and that question. Feel free to investigate. Yeah, think about it.
Okay,
Yeah, that's all I would like to say for the moment. Yeah. So, anyways, my question was: is this proposition, this statement, okay with everybody present here?
Yes, ma'am.
Yes. Then let's provide a quick argument to this. Okay. So what is that we are given? We are given that that the sequence xn is not bounded above. Yeah. Okay. All right. So what does it mean to say that the sequence xn is not bounded above? Since the sequence xn is not bounded above, so I am going to sort of negate the statement that the sequence xn is bounded above. Yeah. So if the sequence xn is bounded above, would mean that there is a real number, some r, such that all the terms of the sequence xn are in absolute value less than or equal to r, right? Now the converse statement would be that for each real number r, there is an index n naught such that xn naught is bigger than that given real number. Correct? Is that okay? All I am doing is just negating the statement that the sequence xn is bounded above. Correct? Is that okay?
Yes, ma'am.
Okay. All right. Now, what do I want to do? My goal is to construct a subsequence of the sequence xn that converges to positive infinite. Okay. So let's do it recursively. So let's choose. So I'm going to choose set r as 1. Yeah. So if you choose r as 1, then the first step is that there exists a positive integer which I am going to label as n1 such that xn1, the corresponding term, is bigger than 1. Right? So what am I doing here? I'm using r as 1. For 1, which is a real number, there must be a positive integer such that xn1 is bigger than 1. Correct? Now, what is it I want to do? I want to construct a subsequence, right? So I want to construct a subsequence xnk of the given sequence xn. Now, so in order to do that, I need to construct a strictly increasing sequence of positive integers nk, right? So I want to choose the next integer n2, yeah? I want to choose n2 such that n2 is strictly bigger than n1, right? So here is my next claim. My next claim is that there exists n2 strictly bigger than n1 such that so of course n2 is a positive integer such that what happens? Such that xn2 is bigger than 2. So does everybody see that this can always be done? Does everybody see that? Everybody with me?
Ma'am, could you please explain
Yeah.
this question?
Yeah, say that one, be a little loud. I can't hear you. Although my microphone, I think, is the speaker is on maximum volume. Can you be sort of repeat your question one more time, please?
Ma'am, could you please tell how are you saying this?
Correct. So what I'm trying to say is that I can always guarantee that there must be a positive integer n2 strictly bigger than n1 such that xn2 is bigger than 2. Yeah. So I'll just write it down. So if not, yeah, if there is no n2 like this as claimed above, then what does it mean? If not, that means that for every integer bigger than n1, we have, what do we have? We have the terms of the sequence xn are at most 2. Correct? Is that okay?
Yes, ma'am.
Yes.
Got it.
Now, if this is true, then the sequence xn is bounded by what? By the maximum of 2 and modulus of x1, x2 up to xn minus 1. Yeah, so let me write that down. This would imply that the sequence x, this would imply that is less than, what do I call it, r naught, where what is r naught? R naught is the maximum of, what is it? So I'll take 2 and x1, x2 up to xn1 So let me see. So do I include the term xn1? Yeah, xn1. Is that okay? Does everybody see this? See, all the terms of the sequence xn from stage n1 are at most 2. So if I say that the sequence xn is bounded by some number r0, I have to take into account these finitely many terms. Which one? x1, x2 up to xn1. Yeah. Take the supremum with 2, you get some positive, some real number. Yeah. And because these are only finitely many terms, and you tell that this is a universal bound for all the terms of the sequence xn, isn't it? And that cannot happen because the sequence xn is not bounded above. Is this okay? Yes?
Yes.
Is this okay with everybody present here? Everybody with me? Any questions? Okay. All right. So, given n1, I can choose n2, and you sort of continue with this procedure recursively, continuing this procedure. So at the kth stage, what do you get? At the kth stage, you are given the nk minus 1, and you choose nk strictly bigger than nk minus 1. So you get a positive integer nk bigger than nk minus 1, such that xnk is bigger than k. Correct? That's how we are choosing these terms. These are by construction. Isn't it? Is that okay?
Yes, ma'am.
Yes. Now xnk is clearly a subsequence of the given sequence xn by construction, right? Yeah. So I will leave you to check that the subsequence xnk indeed converges to positive infinite. So I'll leave this for you to check. Is this okay? Does everybody see this? That this is indeed a subsequence. This is by construction. We have taken care. And this is indeed the subsequence which converges to positive infinite. Just by the definition. All you have to see is the definition of convergence to positive infinite works here. Is that okay? Can I leave for you to check this? Any questions, please ask. Okay, so if there are no further questions, I'd like to go ahead. We have understood what is the meaning of the statement that a sequence of real numbers converges to an extended real number, which is not a real number. Yeah. Okay. I think we are all set to discuss the upper and the lower limits. Yeah, that's the next topic. Okay. So let's see. So we are given, so let xn be a sequence of real numbers, right? And let me consider corresponding to this sequence. Let me consider a set E. What is this set? E is the set of all subsequential limits of the sequence Xn in the extended real number system, yeah, which means the following. Yeah, I'm going to collect all the extended real numbers, which means R union plus minus infinity, such that there is a subsequence of the given sequence Xn that converges to X. Sorry. Right. So what is this set? E is the set of all subsequential limits of the given sequence Xn in the extended real number system. Yeah? So we are allowing all subsequential limits, including positive infinite and negative infinite. Yeah. So for example, take a little example. If I'll write it here, example. Suppose my sequence Xn is given as -1 to the power n, right? Then what would be the set E? What would be the set E for the sequence Xn in this example?
-1 and 1.
It will be 2 points, -1 and 1, correct? There is a subsequence converging to -1. There is a subsequence converging to 1, and those are all. There are no other convergent subsequence of given sequence Xn. Correct? Is that okay?
Yes, ma'am.
Yes. Okay. All right. Here is something that I want to do. See, first thing to note is, so let me define that, and then maybe I'll sort of make a couple of remarks here. Yeah. So given this set E is a subset of the extended real number system. I'm going to make two definitions. So I'm going to define the lim sup. Yeah, so this is limit superior of the sequence Xn as the supremum of the set E, and the limit inferior of the sequence Xn as the infimum of the set E. Right? I'll also write also denoted by, so lim sup is denoted by lim sup or limit and this, or the upper limit of the sequence Xn. And likewise, the lim inf of the sequence, the limit infimum, is denoted by the symbol and the lower limit of the sequence Xn. Anyways, so this was about notation. Let's see, let's go back to this example. So if you go back to this example, what would be the lim sup of the sequence Xn in this example?
1.
It would be 1. And what would be the limit to inferior?
-1.
It would be -1. Yeah. So let's just keep this small baby example in mind. Okay. All right, so let's sort of investigate and spend some time on this set E, right? And one should ask, why are we sort of suddenly interested in lim sup and lim inf? Yeah, why not content ourselves with just the limit of the sequence xn, right? So far, we know what is the meaning of limit of the sequence xn. Whether it exists as a real number, whether it exists as an extended real number. We also have some idea about convergence of subsequences of the given sequence x. Now, why is suddenly a need to consider the limit superior and limit inferior in the sense described above? Yeah. So let's see. Let me try to sort of convince you that this is rather important. Okay. Let's sort of stare hard at the definition of the set E. Yeah. So the first thing I claim is that the set E is always non-empty. Yeah. So given any sequence of real numbers, there is always a convergent subsequence of the sequence xn. So over here, when I say convergent subsequence of the given sequence xn, this convergent sequence may as well converge to positive infinite or negative infinite, not necessarily to a real number, right? So there is, given a sequence xn of real number, there is always a subsequence xnk of the given sequence xn that converges to some extended real number, correct? That's the meaning of the statement, E is non-empty, right? Okay. So let's see this. Before we sort of see some more examples and try to investigate what is happening here. So the first observation is that the set E that I defined upstairs is non-empty, right? Okay, so let's start with suppose that the sequence xn is bounded, right? So if the sequence xn is bounded, then can you say something about the set E? If the sequence xn is bounded, I repeat my question, can you say something about the set E?
It is only real number set without the plus minus infinity.
Correct. That is one thing. More than that, can you say why is this? Can you say so that your observation is absolutely correct? What else can you say about the set E? Can you say in this case the set E would be non-empty? Do you know this?
Yes.
Yes.
And it has a convergent subsequence.
Yes. So what is this result that you are using?
Bolzano-Weierstrass
Yeah,
theorem.
thank you so much. Please don't forget these two important mathematicians. So if the sequence xn is bounded, then thanks to the Bolzano-Weierstrass theorem, we know that there is a convergent subsequence of the sequence xn, and hence the set E is non-empty. I'll write that down. So if the sequence xn subset, so this is a sequence of real numbers. If this is bounded, then by the Bolzano-Weierstrass theorem, then so I will say it follows by the Bolzano-Weierstrass theorem that the sequence xn admits a subsequence, a convergent subsequence, a subsequence xnk, such that xnk converges to some real number x naught. So in this case, under the assumption that the sequence xn is bounded to start off with, this point x naught, which is the limit of the subsequence xn k, clearly it is an element in the set E. Correct? Is that okay? Is that okay?
Yes.
Yes. Now, what if the sequence xn is unbounded? Then what do we do?
Then also there exists a subsequence such that it converges to positive infinity, or it may converge to negative infinity.
Negative infinity. This is what we just discussed in a proposition. Correct? Is that okay? We prove this. So I'll number that proposition something. Let's see. So this is hit. Yeah. So this is. So let me call it proposition A. What is the statement of proposition A? Given any real sequence xn that is not bounded above, there is a subsequence of the sequence xn that converges to positive infinity. Correct? So going back to where we are, if the sequence xn is unbounded, either it is not bounded above or it is not bounded below, or both. It's neither bounded above nor bounded below. In either of these cases, there is a subsequence. So there is a subsequence of given sequence xn that converges to plus infinity or minus infinity. Yeah. So I'll just say use proposition A here, right? So use proposition A to conclude that. Is that okay? So in that case, if the sequence xn is unbounded, either plus infinity or minus infinity, depending on whether it is bounded, not bounded above or not bounded below, or both, they belong to the set E, and hence the set E is non-empty in this case as well. Correct? Is that okay? Is that okay? Is everybody with me up till this point?
Yes, ma'am.
Yes. Okay. See, why am I so interested in asserting that the set E that I define upstairs is non-empty? Because I am talking about the supremum and infimum of the set E. Yeah. So I don't want to sort of wonder about the empty set, right? Okay. Now my claim is that these definitions always make sense. Yeah. So what am I trying to say? That given any sequence xn of real numbers, the limit superior and the limit inferior of the sequence xn always exist. Right? So here is something that we note. Plus infinity is an upper bound of every subset of the extended real number system. Yeah. So what is that we want to say here? I'll just write that down. So if this is a general statement. If S is a non-empty set of real numbers, which is not bounded above in R, then this is a convention that the supremum of S is defined to be positive infinite. Similarly, if S is a non-empty set of real numbers which is not bounded below in R, then the infimum of S is defined to be negative infinite. Right? So the upshot of all this discussion is that the supremum of E and the infimum of E always make sense. Yeah, which means that the limit inferior and the limit superior of a sequence xn always exist no matter what the sequence is. I'll sort of write that in bold. Let's note that down. So, much unlike the concept of limit, the limit of a sequence, the lim sup, the limit superior and the limit inferior of a sequence of real numbers always exists. Is this okay? Does everybody follow this bit? Any questions? See, I'm going deliberately very slow. Any questions, please ask. So shall I assume everybody follows this bit?
Yes, ma'am.
Yes. Okay. So this is advantage over the concept of the limit. For example, you look at this example which we were looking at, xn equal to -1 to the power n. The lim sup and the lim inf exist, but clearly the limit of the sequence xn does not exist. Does not exist. Correct? Right. So if the set E is bounded, then so let me go back to the definition. So if the set E is bounded, then you are looking at supremum. When you consider the lim sup, then you are looking at the supremum of a non-empty subset of the real numbers, which is bounded. So the supremum exists by the completeness property. And if the set E is not bounded above, then we define the supremum to be positive and infinite, and hence the lim sup exists as an extended real number, right? So the limit of the sequence xn may or may not exist. For example, xn is a sequence of bounded real numbers here, what I have written. But still the limit does not exist, but the lim sup and lim inf always exist. Is this okay with everybody present here? So does that mean a yes? Shall we go ahead?
Yes, ma'am.
Yes. Okay. All right. So then, let's sort of see some more sort of observation. It's sort of you work out some exercises, sort of thing. So let's see. Let me sort of write that down. A couple of statements that I'm going to write that down. Statements A. So the following statements are all equivalent. Right. The first statement is, given a sequence xn of real numbers, the lim sup of the sequence xn is positive infinite. Okay. So what is it saying? That the supremum of the set E is positive infinite, where what is E? E is the set of all subsequential limits of the sequence xn in the extended real number system, right? Right. So if the supremum of the set E is infinite, the set E cannot be bounded above. Correct? Is that okay? Which means that the sequence xn is not bounded above. So I'll write statement 2. Is that okay? So if the sequence xn is not bounded above, then we discussed in the beginning of the lecture, then there is a subsequence of the sequence xnk that converges to positive infinite. So let me write that down. This is my statement 3, that the sequence xn admits a subsequence that converges to positive infinite, right? So, if there is a subsequence converging to positive infinite, this exactly means that the point positive infinite belongs to the set E. Now, if the point positive infinite belongs to the set E and I'm looking at the supremum of the set E, then the supremum of the set E must be positive infinite. That is exactly meaning that the limit superior of the sequence xn is positive infinite. Is this okay with everybody? Does everybody follow this? All of them, some of them are actually trivial equivalences. Does everybody see 1 implies 2, implies 3, implies 4, implies 1?
Yes, ma'am.
Yes? Excellent. Shall we go ahead? Shall we go ahead? Okay. I don't get an answer. Oh, this is the same. All right. So this was looking at the case when the limit superior of the sequence xn is positive infinite. Let's look at the following scenario. So what is it that I want to say? So let me write this first. The following statements are all equivalent. Okay, the first one here. So we looked at the case when the limit superior of the sequence xn is positive infinite. Let's look at the case when the limit superior of the sequence xn is negative infinite. So I have E, a subset of the extended real numbers. I am considering the supremum of the set E, and the supremum of the set E is negative infinite. Yeah. So here is a general observation, general remark. So when is so this is a general statement. So if S is a subset of the extended real number system, right? Now I am looking at the case when the supremum of S is negative infinite. Yeah, that's what statement 1 says. So when can be a supremum of a non-empty set be negative infinite? So I'm saying then there are only two situations in which one can have supremum of S to be negative infinite. Everybody with me? So I'm looking at S, which is a subset of the extended real numbers, and I'm looking at the situation when the supremum of this set S is negative infinite. I'm asking, when can this happen? When can the supremum of a set be negative infinite? The claim is there are exactly two situations when this can happen. One, when S is empty. So one is when S is the empty set, or the other one, what is the other scenario? The other one is when S is the singleton set negative infinite. So I'll just say note.
And second one is trivial, but how do we show that if it is empty set, then supremum of S is minus infinity?
No, that's a convention. You don't have to show that. The
Okay.
supremum of an empty set is defined to be negative infinity.
Okay, okay.
There's no sort of, there's nothing to show you. That's a convention that is adopted.
Okay, ma'am.
Yeah. Right? But the point of this is that these are all, there's nothing else. If the supremum of a set is, supremum of a subset of an extended real number system is negative infinite, then it can be either empty set or the singleton set negative infinity, nothing else. Yeah, that is the upshot of this note that I have written. Does everybody follow this?
Yes, ma'am.
Yes, if that is the case, let's go back to statement B part 1. So I am under this scenario, we are looking at the situation when the limit superior of the sequence xn is negative infinite. Please recall, by definition, this means the supremum of the set E is negative infinite. So by this note, this tells me that either the set E is empty or the set E is the singleton set negative infinite, right? But we discussed, that was the first thing that we discussed, that E is always non-empty. So this means that E has to be the singleton set negative infinite. Correct? Is that okay? E is the singleton set negative infinite. This means that by the definition of the set E, there is a subsequence of the given sequence xn that converges to negative infinite, and this is the only convergent subsequence of the given sequence in the extended real number system. Correct? Is that okay?
Yes, ma'am.
Yes, that's the definition of the set E. Yeah. So if you put these two things together, this would mean that the sequence xn itself converges to negative infinite. So I will leave this little bit for you to check. So I will say, how does 2 implies 3? Please check. Now, if 3 holds, if the sequence xn converges to negative infinite, then clearly the set E is the singleton set negative infinity, and the supremum of the set E is negative infinity, which means that the limit superior of xn is negative infinite and 1 holds. Yeah. So 1 implies 2, we have discussed. 2 implies 3, I am asking you to check. 3 implies 1 is straightforward. So is this okay with everybody present here? Does everybody follow this? Any questions, please
Yes.
ask. Yeah. Is this okay? So how many
Yes, ma'am.
audience do I have? 24. One disappeared, doesn't matter. All right with everybody present here? Okay.
Yes.
Yeah. Okay, great. So, we have looked at the case when the limb sup of the sequence xn is positive infinite. The limb sup of the sequence xn is negative infinite, right? Now, the only case to be left to be discussed is when the limb sup of the sequence xn is a real number, right? So, let's look at statement 3. This is statement 3. So let me now say, assume now that, what do I assume? That the sequence xn is bounded above and does not converge to negative infinite. So by assuming that sequence xn is bounded above, I am ruling out the scenario A that we discussed upstairs. Yes. Mind you, we have already established that 1, 2, 3, 4 are all equivalent statement, A1, A2, A3, A4. And by assuming that the sequence xn does not converge to negative infinite, I am ruling out B1, B2, B3, right? So in this case, from the previous points, we know that the limit superior of the sequence xn is actually a real number. This is a real number. Correct? Is that okay? Everybody with me up till this point?
Yes, ma'am.
Okay. All right. Okay. So let's. So this was sort of some discussion. Let's go back to the definition of the limb sup and the limb inf. We consider this set E. Given a sequence xn of real numbers, we consider this set E and define the limb sup, the limit superior or the upper limit of the sequence xn as the supremum of E, the limit inferior as the infimum of E. Clearly, the infimum of E is always bounded above by the supremum of that set. So it follows from the definition that the limb inf is always smaller than the limb sup of a sequence xn. Yeah. So this is a proposition. I'll just straightforward from the definition. So given any sequence xn of real numbers, it follows from the definition that the limit superior so the limit inferior of the sequence xn is always less than equal to the limit superior of the sequence xn. Sorry. Correct? This is just from the definition. So I hope this is okay. I'll write down another proposition. So let xn be a sequence of real numbers, then the sequence xn converges in the extended real number system, converges to a point x of, yeah, so x can be real number or positive infinite or negative infinite also. We now know what is the meaning of each of these statements. If and only if the limit inferior of the sequence xn is equal to the limit superior of the sequence xn. So this is one of the main reason why the concept of the limit superior and limit inferior is important and useful, because a standard approach to proving that a sequence xn converges is to prove that the lim inf of the sequence xn is bigger than the lim sup of the sequence xn. So the fact that the lim inf and the lim sup exist allows one to work with ease and things like that. Yeah. So, I have sort of marked this proposition as a assignment problem for you in assignment 5. So please try this out. Any difficulties, we will surely take it up. So for now, I'll leave the proof as an exercise. Okay, please try this. Leave this proof as an exercise for now. Okay, so what is it I'm saying here? Given a sequence xn of real numbers, the sequence xn converges to a point of the extended real number system if and only if both the lim sup and the lim inf, which always exist, they coincide, and in which case, I'll sort of continue with this, in which case the lim sup of the sequence xn equals the lim inf of the sequence xn. This actually equals the limit of the sequence xn. Is this okay? Does everybody understand what is to be done? What are you required to do here? Everybody with me up till this point?
Yes, ma'am.
Yes? Okay. See, so one-way inequality is always true. Lim inf of xn is less than equal to lim sup of xn. You are trying to show that the other way inequality also holds, provided that you are given that the sequence xn converges to a point of the extended real number system. Okay, so please try that. So I think assignment 5 is problems sort of dedicated to computing limit inferior and limit superior, examples and things like that. Okay, so I think I have a few minutes. Maybe let's do this. there's a sort of another way of looking at lim sup and lim inf. Let me try to sort of do that, or let me sort of instead of trying something new, let me sort of give you another question to work on. I think this will help you understand concepts. Try to show this. Yeah, prove that there exist subsequences so I'll just say subsequence and not subsequences. Prove that there exists a subsequence of the given sequence xn of real numbers such that this subsequence xnk converges as k tends to infinity, and it converges to the limit superior of the given sequence xn. So if you look at, what is that we discussed in the class today, we discussed the following case. We discussed actually some part of this question. We discussed that, so let's look at A. We discussed that if the lim sup of xn is positive infinite, then part 3 tells us that there is a subsequence of the given sequence xn that converges to positive infinite, right? So we had actually did this. We did a solution to this question when the lim sup of the sequence xn is positive infinite. In fact, if the lim sup of the sequence xn is negative infinite, then also we showed that the entire sequence converges to negative infinite. So every subsequence of the sequence xn also converges to negative infinite. What you are required to do is that in scenario C, when the sequence xn is bounded above and does not converge to negative infinite, you have to show that there is a subsequence of the given sequence that converges to this real number. Does everybody follow this? That we actually discussed a lot about this question today, and what is that we did in the class today, and what is that you are required to do? Everybody with me up till this point?
Yes, ma'am.
Yes. If all of this seems too abstract, then next time we meet, we will take up some examples. Yeah, today we did not have time for that. So we will take up some examples next time. So for now, I think my time is up. So we will stop this meeting for now. Thank you all for your attention and time. So I'll stop this.